Hello everyone, I am Ujjwal Pratap Singh, an application engineer from Impulse Technology. In today's tutorial, we are diving into the fascinating world of computational physics, specifically how we solve Poisson equation using something called adaptive meshing. Don't worry if these terms sound complicated. I will explain everything step by step. Before we moving further, let me brief about our company, who we are, who are partner and customer. Impulse Technology is a distributor of next generation technology simulation software like in nanotechnology, nanomaterial, solar cell, organic LED, and lot more. And we are partner with three company. First one is Nano Academic. Nano Academic is a Canadian based company which will offer some software. Like first one is NanoDecal. In NanoDecal, you can perform the modeling and simulation of nanoelectronics, nanowire, and nanomaterial like a carbon nanotube, spintronics device, solar cell, and lot more. Second one is Rescue. In Rescue, you can perform modeling and simulation of large-scale DFT, nanomaterial, and nanoelectronics. You can study on electronic structure, crystal structure, device builder, lattice parameter, nanowire, nanotube, and third one is QTCAD. We will know more about QTCAD in upcoming slide. Second company is Fluxim. Fluxim is a Switzerland-based company which provides world-class software and hardware for photovoltaic device, tandem, thin film, and organic, and light-emitting diode, quantum diode, LED, OLED. And third company is Metra. It is a cloud-based material simulation software. Talking about our services, we are software distributor of next generation technology simulation software training program with our experts. We provide technical support also, and we offer some equipment like probe station, sample holder, battery tester, and recycler strip. And our valuable customer are top pioneer institute of India such as IIT Madras, IIT Guwahati, SRM Institute, and lot more. Before moving to the simulation part, let's talk about Poisson equation. It is a fundamental equation in physics that help us understand electric potential in materials. It also describes how electric charge affect the space around them. And talking about cryogenic temperature, it refers to extremely low temperature, typically below 150 Kelvin. These temperatures are significant in various fields of science and technology, particularly in physics, material science, and engineering. When we talk about mesh, a mesh is like a 3D grid we put over our device. Regular meshes use the same size grid everywhere, but this is an inefficient method. Some area need more detail than other. Now you might wonder, why do we need adaptive meshing? Well, when we try to solve Poisson equation, especially at very low temperature like near absolute zero, the traditional method can struggle. Consider an analogy. Imagine trying to find your way through a dense forest. If you have detailed map only for the clear path, you might get lost in the thickest. Adaptive meshing help us create a more detailed map where we need it most. Adaptive meshing allow us to refine our mesh the area where the electric potential changes rapidly. We start with a coarse mesh and then refine it based on where we see significant change in potential. This means we can focus our computational power where it really needed. If you look at the left diagram, it is a normal mesh with same size grid everywhere. It misses critical variation in potential. In second image, adaptive meshing start with coarse mesh, then automatically refine area where electric potential changes rapidly. To use this technique, we typically need some software tools like QTCAD and GMesh. These tools help us to create and manipulate our geometry file. QTCAD is a computer-aided design tool for a quantum semiconductor-based hardware. It is a finite element simulator used to predict the performance of solid-state spin qubit device. The following features of QTCAD are Poisson solver to find electric potential, band alignment in atom structure, Schrödinger solver, multi-value effective mass theory solver, lever arm calculator, Schrödinger Poisson solver, many body solver, a value stripping calculation tool, time-dependent simulation of quantum control, work at cryogenic temperature in spin qubits. In this section, you will learn about QTCAD workflow. Let's break down the different stages and components. First step is device specification. The first step in the workflow involves selecting the technology and defining the device specification. In this case, the technology being used is nanowire. This step involves to design an arbitrary 3D geometry of the device, meaning you can configure the shape, dimension, and material used in the transistor. This step is crucial because it defines the foundation of the entire simulation. The accuracy of the result will depend on how well the device symmetry is specified. Second step is mesh definition with GMS. The second step in the creation of the mesh, which is representation of the device symmetry in a small element. A mesh is essential. You create that the device into a smaller, manageable section. This is important because the Poisson solver and other numerical work in small sections so calculate electrical properties like potential and charge distribution. This process is known as meshing and finer mesh more accurate result, especially in area where the electric potential changes rapidly. However, finer meshes also require more computational power. And the third step is QTCAD. The third step is running the QTCAD software. QTCAD also come with inbuilt quantum models and material, which means it's already include the physical property and the behavior of certain material and quantum effect relevant to the nanowire. This step done the heavy lifting computation and the flexibility of the Python API allow user to fine-tune their simulation and adapt their various scenario. And the fourth step is visualization and analysis. The final step involves visualizing the result of the simulation for analysis. The result of the simulation can be visualized through like PyCloud, PyVista. Let's jump to the simulation part. PCAD workflow. The first step is create geometry file, where you can configure the shape, dimension, and material used in device. By using this script, I create geometry file with name nanowire adapter geo to generate initial mesh. Script of geometry file contain geometry parameter, bottom drain surface, bottom oxide surface. By running the script in Gmail software, it creates geometry file of nanowire with name nanowire adaptive.geo. If we look at the geometry of nanowire, it has two concentric cylinders. The inner cylinder is filled with silicon and the outer cylinder is filled with silicon dioxide and the outermost layer is metal and the one end is source and the other end is drain. In between the channel is present. This file create two geometry file, a mesh file which is a porous mesh and the geo unrolled file which is has raw geometry information and it will save in meshes file with name nanowire adaptive.mesh4 nanowire adaptive geo unrolled file. During my workflow, the first step is create geometry and second step is mesh creation or 3D geometry of the device. Up to the second step, we have done it. Now, the third step is QTCAD where we define material, boundary, and solver like Poisson solver and Schrodinger solver. Doping and analysis output are defined. Now, let's jump to the VS Code to run the simulation. In this simulation, we import some important module to run the simulation, such as from QTCAD device, we import constant as a city for physical constant like elementary charge and Planck constant for calculation. In the same way, we import mesh 3D for creating 3D mesh structure for the device, I/O for input and output operation, analysis used for analyzing device characteristic, material is used for material specific properties, and the device is used for the define the structure of the electronic device. In the same way, Poisson is used for the Poisson equation solver and its parameter. Defining device parameter VGS. VGS is a voltage applied between the gate and source terminal of the device. Here it is 2 volt. After that, we define metal work function. the electron affinity of silicon and material. Here and the material silicon and electron affinity. After that, we define band gap. After that, we define device height in nanometer and device radius in nanometer. After defining the device parameter, now we turn to part 2 mesh file and output file. Setting the script directory. Script directory is equal to path live dot path in bracket file parent dot resolve. Path live path a module for working with file path, and file represent the current Python script file path, and parent is used to get the parent directory of the script, and dot resolve which used to convert it into an absolute path. After that, we define the location of the mesh file which contains the device mesh structure. After that, provide additional geometry related data needed for the simulation. Now it's turn to load the mesh where computation happens. Define the scaling factor. Its purpose to convert the mesh dimension from meter to nanometer for nanoscale device simulation. A mesh class is used to create a 3D grid structure for the device, and the scaling is used to specify the mesh dimension, and path mesh specify the file containing the mesh data. Its purpose to load the post mesh from the specified file, preparing it for a device region. Now it's time to create device from mesh and set temperature to 10 millikelvin. Create a device object at a device class representing the simulated device, and mesh the mesh structure loaded earlier. Here configure the device to simulate electron as a charge carrier and set temperature to 10 millikelvin. After that, create device region. Here new region is add a new region to the device, and channel oxidation and source oxidation name of the oxide region, and material is use silicon dioxide for the region. After that, channel source and drain is defined where material is silicon, and doping is defined where p-doping is defined, and concentration is 0. After that, create an adaptive mesh for a non-linear Poisson solver. After that, we use self-consistent solution and then plot a band diagram. Let's run the simulation. The adaptive mesh of the nanowire, and some Poisson iteration happen from 1 to 12 iteration happen, and some relative error and error threshold. Again, some Poisson iteration happen, and it's load the band diagram where red show a conduction band and valence and Fermi level, and distance in nanometer and energy in electron volt. And that's it. By using adaptive meshing, we have achieved a highly accurate solution to Poisson equation with a balanced computational load. Adaptive meshing is a powerful technique that is essential for the simulation in complex device, especially at lower temperature. Thank you. If you have any query, contact us at